Hi everyone and welcome to another lecture. Today we want to talk about determinant of a matrix. So let's get started. So first we need to talk about what is a determinant. A determinant is a scalar, that is a number, and it contains some encoded information under linear transformations of that matrix. What I mean is that let's say you have a matrix called S and you do some linear transformations of it. So this determinant captures some invariance of some features of S under linear transformations. This will be more clear when we talk about an example. Next thing we want to ask is, when is a determinant defined? This is the second question we are asking. So can we do determinant for any matrices? That is, can we compute determinant for any kind of matrix? Let's say you have a matrix like this, 1 2 3 4 5 6. Can you compute a determinant from this? The answer is no. Determinant is only defined for square matrices. So if I had a matrix like A, that is 1 0 2 5, for this kind of matrices there is a determinant. Determinant of A exists. So can you do a determinant for this? Let's say B, take it to be a column matrix 1 2 3. For this, determinant of A does not exist. Now let's try to see how we can compute the determinant of a matrix. Let's take a 2 cross 2 example, that is our square matrix of 2 times 2. Let's take it 1 2 4 7. So the idea is to start from anywhere. That is, you can either start from this row, let me choose another color, this row, and if I do that, the first thing I need to do, I need to take this number over here, that is the 1 1 element, that is just 1. So you write that, and then you have to look what is the element across it, that is this direction, diagonally. This is 7, right? And you multiply them. Then you put a minus sign. The reason for minus sign will be explained in a few seconds. You have 2, right? And then you look across diagonally and you see 4. So you type 2 times 4. If you evaluate it, this is just minus 1. So what did we do here? Let's clarify in details. So let me write this matrix again so that you can see what I actually did. So I started working with this row, and when you start working with this row and you take this element 1, then you have to forget about this row and this column, both of them. You forget them, and the only thing that remains is 7. Similarly, when you work with 2, that is the 1 2 element, you forget about first row and the second column, that is this row and this column. So in general, if you had a n cross n matrices, matrix, and let's say you have it like this, a1 1 a1 2 da 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 a1 n, and there are more over here. If you start from here, you take this element first and you forget about the corresponding row and corresponding column. That is, when you take 1 1, you forget row 1 and column 1 exists. So this is the first step, and then you do the rest. Returning to our 2x2 example, because we will deal with some more examples, and then you can go on and compute n cross n. In general, this is a very long computation if you want to do it by hand. So again, let me write my matrix again, A 1 2 4 7. So the first step is to forget about the rows and columns. But you might ask, where is this minus sign coming from? That is this one. So there is a general rule called the -1. The general rule is like this: you have a -1 R plus C. So this row, that is R, and C, that is the which row you are working on and the which column you are working on. To make this more explicit, let's calculate the determinant of A again. So first I write this 1, right? And there is a sign problem, and this sign problem is fixed by this rule. So first you write -1, and this is in the first row and the first column. This is the 1 1th element, so plus 1 and place 1, so this is just 1 plus 1 2, and then you write this guy 1, and then you forget about this row and this column and you multiply with 7, right? And then you put a plus sign in general, and then you put -1, and since you are now working with number 2, that is on first row and second column, you write 1 plus 2, and you take this element and multiply with 4. Again, you can see this is just 7 minus 8. This is -1. This will be more clear. So let's take another example, and this time let's try to do it for a 3x3 matrix. So let's take a 3x3 matrix as P, and let's say this is 1 2 0 0 1 5 9 0 7. Now again, let's work with the first row. So the first element is our sign fixer, that is the, by first element I meant that the thing we want to write first. So I want to write -1, and then I type the row and the column number. But then if I forget this first row and the first column, I can see that there is still a matrix left, right? So I write it like this: 1 5 0 7. That is, I have to compute its determinant, and let's just put it under this modulus sign. And then again, when we are working with 2, this is the 1 2 element. 2 is on first row and second column, so the R value is 1 and the C value is 2. So you put a plus, you put a -1 to the power 1 plus 2, and again, when you forget the, let's say, this row again and this column again, you can see that if I forget them, there is a matrix of 0 5 9 and 7. So let's write that: 0 5 9 7. And finally I want to write, this is what? This is a 0, right? And it is on first row, third column. So the R value is 1 and the C value is 3. And this is 0, but we know that we are multiplying with a 0, so everything will be 0, but still let's write it explicitly so the picture is clear to us. Let me use another color. So again you are forgetting the first row, and now you are forgetting the third column. When you forget the third column, this is the matrix you have left, a 2 cross 2 matrix. So let's write it 0 1 9 0. Then evaluate it. This is what? 7 minus 0. The second guy, we evaluated this. The second guy is giving us a minus 1 first, because 2 plus 1 is 3, and you have 0, and 9 times 5 is 45. Again, remember that we are evaluating the determinant for these matrices. These are 2 cross 2 matrices, and we saw in the above example, that is here, on how to evaluate determinant for 2 cross 2 matrices. So this will be minus 45. And finally 3 plus 1 is 4, so this is just plus, and this is a 0, this is a 9, and you have 0 times plus 1, and this is just minus 9. So this is just 0, right? And this is 7 plus 45, 52. In this way, you can evaluate determinant for a 4 by 4 matrices as well. That is, you have a matrix that is 4 by 4. I'm not writing any terms. Let's just say there are some numbers over here or some symbols. The idea is to take one element out, reduce it to a 3 by 3, and then evaluate this 3 by 3 matrices determinant. So ultimately you will have to reduce down to 2 cross 2. So as you can see from this schematic diagram, that evaluating determinant by hand is very difficult, especially if your matrices are of really higher order, let's say 6 cross 6, 5 cross 5 and stuff like that. Even in 4 cross 4 it takes a lot of time. So let me get rid of this. Now let's talk about something called minor. So what is a minor? That's the first question we will ask. Notice that in a 3 cross 3 matrix, when we try to evaluate the determinant, we had something like, let's say you have 1 4 minus 2, a 3 cross 3 matrix, 0 minus 1 2, 3 5 minus 3. When you try to evaluate this determinant, the minor for a specific element, let's say I want to have the minor, that is the minor for the 1/1th, the 1/1th element. So how do I figure that out? So you take this 1/1 element, you forget this row and column, and then you took a look at this part, and this part's determinant gives you the minor. It is as simple as that. For example, in this case, the 1/1th element is 1, and if you calculate the determinant of this part highlighted over here, it's 3 minus 10, that is minus 7. Similarly, you can calculate minor for the other elements as well. For example, if you wanted to calculate minor for this element over here, I'm highlighting by the blue color, that is the element on row 2 and column 1, that is the 2/1th element. So how do you do that? Forget about this row, forget about this column, the rest you have is this, that is 4 minus 2, 5 minus 3. So if I write that out, I have to evaluate the determinant of 4 minus 2, 5 minus 3. If you evaluate it, you get the minor for the 2/1th element. And let's talk about another thing right now, and it's called a cofactor that is related with the minor. So if you want to evaluate the cofactor for any element, you just have to multiply the minor of that element with minus 1 to the power r plus c. This is how you can evaluate a cofactor. For example, if I wanted the cofactor for 1/1th element, you just have to put r equals to 1, c equals to 1, and you calculated the minor before, that's minus 7, and the result is minus 7. That is, this is the cofactor. This is how you can calculate cofactor and minors. And the reason we discussed this in this lecture, because in the next lecture we will talk about inverse of a matrix, and because in the upcoming lectures we will talk about the reason we discussed minor and cofactor, because in the upcoming lectures we will talk about inverse of a matrix, and we will see that minor and cofactor will play an important role while evaluating the inverse of a matrix. So that is it for today, and I'll see you guys on the next lecture. Thank you.